Right, so welcome to this second part of week 10 on quantum statistical mechanics. In the last video, what we've seen is that when you mix quantum and classical probabilities, the way you do it is by introducing a sample space where the actual outcomes of your probabilistic experiment are actual quantum states themselves. Okay, and so here we see that there is some probability having to do with the probability of being in a certain quantum state, but when you are in a quantum state as well, then you've got some probabilities of of having a particular outcome if you measure it with a given observable. Okay, so in general, that's how that happens. So that's the reason why I need to introduce a new concept here, which I call super averaging. Okay, now if you look super averaging on Google, you won't find really what I'm going to talk about. But for lack of a better word, because there is no actual word for it, then I'm using super averaging because it sounds kind of cool. So let's assume you've got psi1, psi2, psi3, which are elementary events. And here in principle, that can be general, so you don't need to have that these elementary states or events are necessarily related to some observables, for example. Not necessarily. Elementary events with probability probabilities P1, P2, P3. Okay. Then we define, then the so-called super, and here I would call that expectation values, super expectation value of an observable O, is defined as the following quantity, and that's kind of very important. So it's defined as, so that's like this. So I put some double, wedges. So that's how this is defined. That's how it's denoted, and that's the sum over I. So it's the number of states in my sample space, and then pi, and then psi I O psi I. Okay, and now what we are going to do is try to understand what this expression actually means. So this is the quantum expectation given psi I. And then this bit here is the classical probability to be in state psi I. Okay, so we see that this particular expression is literally, but like literally really, a classical average of a quantum average. Okay, so that's why it's a super averaging, because there are two averages. You need first to account for the quantum average, and then basically you look at the probability for this quantum average to be there in the first place. So it's a weighted quantum average, if you will. Okay, so probably this formula in itself deserves its own framing in a big box. Okay, because it's a definition, so it's a super important definition of what super averaging is about. But if you understand what this definition means, then you understand how to mix together quantum and classical probabilities. Okay, so there is one thing that can be noted as well, is that as a remark, but that's an interesting one, is that if psi I, okay, is, as we said before, for example, okay, AI BI, okay, then one will get the following. Okay, so that would be the super average of some observable A, for example, but A here is related to the variable, to the number AI here. Okay, so that would be sum over I and then PI, and then you've got, let's say, AI BI, then A, and then AI BI. But then it turns out that this A here, that is acting on this guy here, will return simply AI. Okay, so you will get that this is sum for I and then PI, AI BI, and then you've got essentially AI BI. But AI is just a number. Okay, so essentially what you would get is sum I, then PI AI, and then you've got AI BI, AI BI, okay, which is equal to 1. So in the end, if your states in your sample space are eigenvalues, I mean, exactly as I said, so a collection of eigenvalues or eigennumbers related to commuting observables, then you get that the average of A is PI AI. Okay, so that's literally what you would expect, right? So AI is one of the possible values that is measurable, and basically you just say, well, you know, if I'm in a given quantum state and that time that is eigenvector of it, then probabilities of that eigenvector will directly set, which is this one, will directly set the like the average of my actual eigenstate, okay, of my actual observable. Okay, so that's something that matters very much in what we are going to do also afterwards. So the bottom line of this discussion here is if psi I is an eigenvector of, let's say, A, but you know that can be any kind of observable, then superaveraging becomes a normal average. Becomes a normal, if you will, average running over all possible eigenvalues. So it's as if the sample space now became the space of eigenvalues of A in a kind of classical probability theory, and then you've got the corresponding probabilities. So all possible eigenvalues of A, and with probabilities Pi and I ranging from 1 to however many eigenvalues you have. Okay, so that's how you do it, really. And again, I think this is important to keep these things in mind, that there is this notion of superaveraging, and that's how you basically put these two things together. Now, this thing is done formally in a slightly different manner by incorporating something called as a density operator. So I'm going to introduce how that works, this density operator, how does that come to be with the definition I've given so far. So again, here I'm saying that if you know or understand how this superaveraging works, then you understand how to obtain the density operator. Notion of density operator. Alright, so we start from the basic formula, start from superaveraging of some arbitrary observable O, okay? And then we have the following, so we've got O is equal to the sum over I of pi and then psi I O psi I. So far so good. Now what I'm going to do is first recognize that I can put this guy over here, okay, just next to O, because it's a number. Pi is a number, so I can put it wherever I want in this equation. Okay, so this is a quite standard kind of trick in quantum mechanics. If you've got a number, you can put it wherever you want. So here I have this, so I've got psi I, O, then I've got this pi, and then I've got psi I now, okay? Now what I'm going to do is clearly not necessarily trivial, but that's what we are going to need, is basically realizing that this pi psi I can be written in a more complicated way as follows: sum over j, pj, and then psi j, and then psi I. Okay, so that's basically a more complicated way of writing it down, but that's equivalent mathematically. Now this is equivalent if, so here I need to say if psi j psi I is equal to delta ij. So here I'm assuming that this all this sample space, these guys are orthonormal, from an orthonormal basis. Okay, if that's not the case, then I can't write this down this way. Okay, so if this is the case, then this is delta ij, that's a Kronecker delta, and then I can replace by like substitute this expression, so substitute this, okay, into this part here, and I will obtain the following equation. So that's sum over I, and then I've got psi I, and then O, and then I've got the sum over j, pj, then psi j, and then I've got psi I. Okay, and now I'm going to define this as being equal to the sum over I, psi I, O, and then I'm going to call that rho, psi I. Okay, and here I've defined rho, which is equal to the sum over j, pj, psi j, as being, so rho is called the density operator. Okay, or sometimes it's called as well density matrix. It depends on the books you are looking at. So that could be directly quantum mechanics textbooks or statistical mechanics textbooks. Now what we have in the end is that therefore the average, so let's put this again, this is a very important definition. It's a tool that helps us characterize mixing quantum and probability theories, and what we get as a result is that the average O is therefore equal to the sum, so this is something I'm just rewriting, psi I O and then rho psi I, but this is basically the same, and that's a very common way of writing it down, as the trace of the linear operator O rho. Okay, so that's the final result we'll finish with in this particular video, and in the next set of videos we are going to look at what these things actually does. So one final thing I've got to write down is simply that the density operator, okay, fully captures the probabilistic character of a problem, and that's a point here, of a problem, be it quantum or classical, so it does both. Okay, so that's it for this video, and next time we'll see how do we use this particular thing to do statistical or quantum statistical mechanics. Right, okay, so see you next time.